Welcome back. This is lecture 35. So, as promised, I was supposed to start on transmitter side architectures in this lecture, but I realized that there is a small part of the passive mixer on the receiver side that was missing. Maybe I'll spend a few minutes on that before we move on to transmitter. So, when we were doing noise analysis for mixers, what we essentially did, or rather, what I essentially focused on, was the noise from the source, right? So basically for noise analysis, I don't require this source. I basically said that you have some architecture like this, and it goes into some low impedance node, and the noise from this resistor, gets also mixes, and you have noise folding, and thereby you get an increase in noise flow, right? And we also saw that conversion gain is contributed by only C1, whereas noise is being contributed by summation of C0 squared, C1 squared, C3 squared, and so on, right? So that is fine. So that note that while doing all this analysis, we only assume that the noise is coming from this source, right? But in principle, what I missed mentioning was how are these switches made? These switches are also made using transistors, right? And the transistors are in linear region, right? So these transistors are in linear region, which means this MOSFET in linear region, which essentially means that there is a channel here through which there is a channel where I have bunch of inversion charges available, which gives some resistance, and the value of the resistance is how much? So this is a channel which has a resistance, and this value of the resistance is approximately 1 by mu n C ox W over L times V over drive, right? So this is R on. So which means that you are going to get a thermal noise equivalent to this R on. Right? There can be some extra factors which depends on the profile of the charge in the channel and so on, but you are going to get thermal noise because of R on, right? So essentially, I can model these passive mixers as this resistance of the previous stage, right, which is R in, and I have R on and an ideal switch. I have R on and an ideal switch, and so on, right? And since the signal and since all these switches are non-overlapping, right? So essentially the signal or the noise, what you can consider, either flows through this path, or they flow through this path, or they flow through this path, and they do not share the paths, which essentially means that I can effectively say this is equivalent to a resistance of R in plus R on, or instead of saying R in, let me say RS, source resistance. That is a better way of expressing this, and an ideal switch. So these are ideal switches, right? And by doing so, what we did, we essentially simplified our noise analysis, right? So, and we can assume that all the thermal noise is now being contributed by both RS and RR, right? Okay, fine. So this is something that I wanted to mention before we move on to the transmitter part. So now let's switch our focus to the transmitter side of the receiver, of the transceiver, right? So, so if I have to draw the entire thing right now, what did we have? We had a filter, we had an antenna, then we had all sorts of image rejected SAW filter and LNA transmission line. Then we had a mixer. This input was at FLO. Now, depending upon whether you have a zero IF receiver or a heterodyne receiver, you might want to have a low pass filter or a band pass filter. And I mean, the part that we did not cover in detail, but it should not be very difficult to visualize this, is that if your IF frequency is large, right, then which essentially means that the FIF that you get here can be, let's say, 500 megahertz or 1 gigahertz or so on, which essentially means that if you have to down convert it again, I mean, if you have to process it, you might want to down convert it again, right? So a second stage of similar mixer topologies are often used, right? So, I mean, the analysis and everything remains the same. Just the design considerations of the subsequent stages are much simpler, because you have gain in the previous stages, and you do not have to bother about LO feed through and so on and so forth, right? So we'll not go into too much detail with that. So we assume that here we are getting the baseband information. We get FBB, right? So this is, and after this, what you do? You normally pass it through an ADC, and you get bits. Once you have a bits, you store them in a memory. So that's generally that is done. And once you have a bit, and you can do whatever you want, right? And then what is the transmitter side of the picture? The transmitter side of the picture is that you have a signal at baseband, right? So in other words, you have a memory which has bits, and these bits, from these bits, you convert these bits into an analog signal through a digital to analog converter, right? And the rate at which this analog to digital converter is clocked will be FBB, right? Or you can call it an intermediate frequency or baseband frequency or whatever. The DAC will be clocked, will essentially determine the fundamental frequency of the signal that is coming out of the DAC, right? Okay, so because this is not a data conversion course, so we will not get too much details into this. But what eventually happens is, just like when you do an ADC, you have to do a first sampling and then digitization. Similarly, in case of a DAC also, there is some inherent sampling kind of operation that is inbuilt, or in other words, in this case, you have a sample and held waveform that generally comes out. So in other words, you end up having this staircase like waveform at the output of the DAC. Now, depending upon the type of DAC, you have different types of waveforms. Now, you might want at the output of the DAC, you might want to filter it, right? Or you might not want to filter it. Depends upon what type of blocks that generally follow the DAC. But in order to keep pace with, or in order to keep the symmetry between the receiver side and the transmitter side, we'll assume that there is a filter, right? So let's say there is a filter. There is a low pass filter which smoothens out the DAC output, and you get like pure sinusoid or modulated sinusoid kind of output. Okay, so this is at FBB also. So here you get FBB clocked at FBB and harmonics of FBB, right? So I'm not writing that, but plus other tones. Right. So here you, let's say, put a bandwidth of FBB, and at the output you get only baseband signal. And then what? So now you are kind of here. This is the equivalent with respect to the receiver. Now what do we do? So you have to put a mixer, right? And you multiply with a signal which has a fundamental frequency of FLO. But now we know that this will not be FLO only, you will have a square wave and so on and so forth, right? And then maybe you put so here you get all sorts of signals. You get FBB plus NFLO. So which one is of interest? Obviously now we are transmitting, that is we are translating this FBB into higher frequency. So we would like to have a band pass filter around FLO, right? We have band pass filter around FLO, and then you ultimately pass it through another amplifier. We call this a power amplifier, and then pass it through and send it out through an antenna, right? So this is the typical transmitter chain, which is basically the inverse of a receiver, right? So now, just like in a receiver, right, we saw an issue with image reject. Just like in a receiver, we saw issues with the image frequency get down converted. Here we can have a problem where, right, where the image, I might be taking up signals, I might be taking up the spectrum while transmitting the image also. Why? Because note that here you don't get FBB only, you get plus minus FBB, which means here you are transmitting NFLO plus minus FBB, right? So here you get FLO plus FBB and FLO minus FBB, and both of them are carrying the same information, which essentially means that I am taking double the spectrum while carrying half the information, and that's useless. So is this problem, how did you tackle in the receiver side? In the receiver side, here we had FLO plus FIF and FLO minus FIF. We rejected one of them by putting IQ mixer. So here in the transmitter side, we'll prevent the generation of one of them by putting an IQ mixer, right? So now we know how a mixer works. Since we know how a mixer works, we can readily go about talking about it without giving too much of introduction. So let's, what was the first thing that we did when we were doing mixers in the receiver side? We talked about single balance and double balance mixer, right? So here also in the transmitter side, we will also have a concept of single balance and double balance mixer, and the reasoning will be similar. So in the transmitter side, as you will see, so when I write it out, it will become more apparent. So note that in order to appreciate the need for the single balance, double balance, and IQ mixers, so let's start with single balance, double balance first. So what is the spectrum here? The spectrum here is close to DC, right? This is close to DC. This is baseband signal. If I'm interested in sending voice signal, this is like sub kilohertz range, right? So it's close to DC. Even if you are talking about video signals, it's like few megahertz range. It's not as if we are going to like hundreds of megahertz and gigahertz, and so there are applications for those cases also, but we are not talking about those applications. We are talking about these scenarios where this signal that the message signal, the baseband signal that we are planning to transmit is close to DC. Now, why is it important to recognize this? It is important to recognize this because if a signal, if the AC part of the signal is close to DC, then I cannot uncouple the DC from the AC by using a decoupling capacitor. Why cannot I do that? Because the size of the decoupling capacitor will become astronomically large. The RC time constant associated with the decap will be astronomically large, and which might not be feasible for an integrated circuit based implementation, right? So hence we'll have to live with the fact that the DC comes in along with the message signal, right? So your message signal or the baseband signal will have a component of VDC plus some baseband signal VBB cosine omega VBT, right? So now let's say you pass it through, you multiply with a sinusoid, right? If you multiply with a sinusoid, what do I get if I simply multiply with a sinusoid? Or rather, in this case, cosinusoid, cosine omega LOT. What do I get? I get VDC cosine omega LOT and plus VBB cosine omega BBT times cosine omega LOT, right? So now what is the spectrum of this? Clearly you have a spectrum at omega LO and you have a spectrum at omega LO plus minus omega BB. This is on the positive side, right? Omega LO is much greater than omega BB, so on the positive side we get these three. Now, since omega BB is close to DC, as you can see, these three are very close by, and out of which this waveform is not really carrying any information, but it is basically carrying the DC information. And I'm unnecessarily taking up a spectrum while basically transmitting DC. Right? This VDC does not have any information, but I am still taking up a spectrum at omega LO. Right? So this is again the same similar thing. This is like a LO feed through that goes through. Right? So what is the possible solution? The possible solution, just like we had in case of this is the equivalent of a single balance mixer. So we can have a double balance mixer. What do we do? So if I have a negative signal available, but note that the DC voltage cannot be negative. DC is always DC, and on top of that, I can have a positive or a negative swing, right? So essentially, if I have a VDC minus VBB cosine omega BBT, and I can multiply it with cosine omega LOT, here what do I get? I get VDC cosine omega LOT and minus VBB cosine omega BBT times cosine omega LOT. Correct? So now if I do a subtraction of these two, right? If I take this and do a subtraction, then what do I get? The VDC terms cancels out, and I am only left with 2 VBB cosine omega BBT times cosine omega LOT, right? So this does not have any signal at omega LO, right? So this is the equivalent of a double balanced mixer on the transmitter side. So no omega LO. Correct? So what did we need for this? We needed a negative signal, which we can easily get, right? Because the signal we are generating is from within the chip. The baseband signal is within the chip. I can generate a differential version of it and then feed it, right? And then subtract it. So how can I do this subtraction? So note that ultimately the mixer will be followed by a power amplifier, an amplifier, right? Which means an active device is almost always essential. So once you have this, once we recognize this, then this addition becomes quite trivial. So this is VDC minus VBB cosine omega LO, plus, and this is VDC minus VBB cosine omega LOT. Omega BB. I am not writing it correctly. Yes, it is. And this I am feeding with cosine omega LOT, and this I can maybe send to a voltage control current source, output of which I can connect directly because this is the current source, right? And this can be plus, the other can be minus. So I essentially subtract in the current domain and I pass it through a resistor, right? So here I have no omega LO, right? So this is equivalent to a double balanced topology. I mean, you can now play around with the switches. You can put switches in appropriate places, but you now should be able to appreciate the fact that here, even though I have no omega LO, I have signals at omega LO plus omega BB and omega LO minus omega BB. But note that both of them are sending the same message signal, right? So again, I am taking up double the spectrum while sending one information equivalent to one channel, right? So not a very efficient, or rather it's a terribly bad way of implementing a transmitter, correct? Because spectrum is extremely costly. So how do I go about fixing this? If you recall, again, just like in case of a receiver, we use IQ mixer, right, to reject image. Here we are going to use the IQ mixer to prevent generation of the image signal. In this case, either we will have this omega LO plus or omega LO minus and not both, right? So how should I go about doing it? again in a very block diagrammatic point of view. Now I am not going to show you the VDC part because I know I can always do this negative subtraction and all, right? So given that we understand that, I will only show you the signal part, right? How to go about prevent generation of the LO, right? So what is the root cause? The root problem is we are having a signal VBB cosine omega BBT, and I am multiplying with cosine omega LOT. So this is generating the signal BBB cosine omega LOT times cosine omega BBT, which means I can break it up into cosine omega LO plus omega BB plus cosine omega LO minus omega BB. Correct? So now you should readily be able to tell me, if I have to get rid of one of these, what do I need and what should I do? So clearly I need cosine omega LO plus omega BB minus cosine omega LO minus omega BB. Correct? So then I can add them so that one of the terms can go off. So in multiplicative form, what is cosine omega LO plus omega BB minus cosine omega LO minus omega BB? It is basically sine A sine B, right? Sine omega LO sine omega BB. Correct? So essentially what we need is BBB sine omega BBT, and here I shall multiply with sine omega LOT. Correct? So here I get BBB at 2 cosine omega LO plus omega BBT minus sine omega LO minus omega BBT. Correct? And then I add them up. If I add them up, what do I get? I get BBB cosine omega LO plus omega BBT. Right? So here no image also. Correct? So this is essentially, you get rid of that sideband, and this is essentially equivalent to IQ mixer. Now how do I get this? How do I get this omega sine omega BB? So obviously when you have a bunch of memory, so I said that you take this and pass it through a DAC, right? And the DAC is clocked. Correct? So you take the same bits and pass it through another DAC, which is clocked. If this is S of t, S DAC t, you make sure that this is S DAC t minus t DAC by 4. Right? So, or TIF by 4 or whatever, right? So so essentially I need a quarter cycle delay. If I modulate the input signal with a DAC which is driven by a sinusoid, let's say it is sinusoidal DAC, let's say, and in one case I am multiplying with sinusoid, another case I am multiplying by cosinusoid, right? So in case of when I do not have sinusoids, I have square waves. It is equivalent to saying I have one square wave which is quarter cycle delayed with respect to the other. So the output will be so typically the nomenclature is, this is called IDAC, in phase DAC, and this is called QDAC, quadrature DAC, right? So here, I mean, if I put a filter, low pass filter, so this will be VBB cosine omega BBT, and this will be VBB sine omega BBT. Correct? And then you put your switches. And how do you go about putting your switches? So you have, this is BBB cosine omega BB. So you have a switch here which is being driven by ST. Then obviously here you have BBB sine omega BBT. which you are being, let me call this S0T and let me call this S90T, right? And obviously to ensure that you do not have the DC signal also, if I say I have VDC plus, I have VDC plus, so you connect these two. Here you have, let's say, VDC minus VBB cosine omega BPT, and I call this S18TT, and here you have, let's say, VDC minus VBB sine omega BBT. I call this S270. So the subscript refers to the amount of delay they have with respect to each other, right? And then you pass them through some sort of resistor or some sort of impedance. I should not simply say resistor because it's not a low pass thing anymore. You want to pass it through an LC, it's possible, centered around FLO or omega LO. Right? And then you take them and pass it through. You can pass it through a differential. You can pass it through a block which gives you a differential gain, or you can pass it through. You can pass it through two different voltage control current sources, and then eventually feed it to a load. It depends on us, right? So note that this is the important thing to note here is that I did not explicitly specify what is being driven by. So I did not explicitly specify what is the output impedance of the DAC or the low pass filter. So this can as well be a current driven source or a voltage driven source, but the treatments are different. That is what we are going to look at next. So if this is a voltage driven source and these switches are only acting as a switches, as in obviously they are only acting as a switches. So if this is a voltage driven source, and you assume that there is so if this is a voltage driven source, then if you simply connect it like this, what are you essentially assuming? We are assuming that the impedance looking this side is much smaller than the impedance looking into the load, right? So so essentially what we are banking on is the fact that something like this is happening. So if you have a voltage source, let's say I call this V1, I have another voltage source, I call this V2, and I have some resistance R and R, and I connect them. What do I get here? I get V1 plus V2 by 2, right? So that is what we are banking on here, right? So in this case, block preceding on the block on the left hand side from where this VDC plus VBB cos sine omega LOT and all those things are getting generated, so that is equivalent to being driven by a voltage source. Then we were assuming that the resistance looking this side is much lesser than the resistance looking left, right? So in other words, what we are saying is we have a resistance here, right, and you have a load here. Obviously this output is going to get modulated, will not be equal to V1 plus V2 by 2. It will be something different because now you have to take the loading into account. But if this guy is at resonance, right, if this guy is at resonance, then it will effectively be equal to V1 plus V2 by 2. But we know that it is not trivial to make perfect resonance. So there will be a Q associated with that Q factor associated with that inductor capacitor parallel topology. So you are going to get some loss, right? This essentially is doing is this is giving you an idea of a up conversion. This is doing an up conversion through a set of passive IQ mixer, right? So this is quite simple and it works. But the important thing to note here is that this only works if there is no coupling between the in phase path and the quadrature path. What I mean, this is the in phase path, right? This is the in phase path, this is the I path, and this is the Q path, right? So if there is some coupling between the I path and the Q path, then obviously you will not have you will not have that IQ separation, right? Which essentially means that just like you cannot have perfect image rejection when you have I and Q at the receiver and getting combining, you will not have that scenario where we get no image at all, right? So depending upon what is the accuracy between the I and the Q path, right? What is the driving capacity between the I and the Q, what is the matching between the I and the Q path, you can get certain amount of image, which means that the component at omega LO plus omega IF can be present, but the component at omega LO minus omega IF will not be fully gone, right? Because there can be some coupling. And one practical problem that happens is that invariably these two lines have to be routed closely because they are going into some differential amplifier somewhere on the chip, right? So you are invariably have some capacitance between these two lines. Moment you have this capacitance, they almost always couple, which means that you do not get perfect image cancellation, or you do not get a scenario where the image is nulled, right? So if somebody is looking to design an IQ upconversion mixer, so you have to be very careful with this coupling. Otherwise, you will get a fairly non-negligible amount of signal at the image band, right? Which will not be a good thing to deal with. Okay, while this type of mixer works and it's perfectly fine, but the problem with this is you do not get enough gain, right? In fact, you do not get any gain. So all the gain is now being asked by the final stage, which is a power amplifier, which we'll get to from the next class. But the key problem with a passive mixer is that do not have any gain. Now, how do you get a gain? And we saw it in the receiver cases also. You go to an active mixer, right? What is an active mixer? You, instead of driving through a voltage source and then switching, you drive through a current source, right? So what I mean is, you have let's say you have an IDAC. So, or rather, I'll start from VBB. Let's say you have VDC plus VBB. So you pass it through a common source amplifier. So this current is I naught plus GM times VBB, right? And then you pass it through a bunch of switches, right? So if you have a switch here, let's say this is ST, you have a switch here, you call it S bar T or ST minus, whatever you want to call it. Then let's say, and if you want double balanced, obviously you will require here VDC minus VBBT, right? And here, let's say this is ST, this is bar T. Okay, so this current here, as usual, is I naught minus GM times, not negative, just to ensure that this is minus GM times VBBT, right? So S and S bar T are complements of each other. So the current that flows through here, right? Yeah. So you end up connecting these two, and you end up connecting these two, and let me draw it carefully, right? And you connect a load, and you take the differential, right? And that essentially becomes your active mixer, correct? Now, how do you get a gain? You get a gain because the current here, the current that you are pushing in is GM times VBBT, and if the load here is some ZL whose real part is RL, then the gain that you are getting is GM times RL times VBBT, and then the conversion gain, that is because you have times basically the C1, right? C1 as in the fundamental component of the switch, right? So that essentially is the difference between a passive mixer and an active mixer. And how do you make S of t? You make S of t by just like earlier case, you make this. You use a transistor, an NMOS transistor per se. Here you have, by the way, this is a double balanced topology. This is not necessarily an IQ mixer. If you have an IQ mixer, you need a set of that, this entire thing, another set, and clock everything with 25% duty cycle, right? So that we should always keep in mind. So this is S of t, this is S bar of t or SB of t. If I call this S of t, this bar of t, this goes here, this goes here. I mean, this can as well be an LC tank, and you have a capacitance between them to give you the tank response, right? Okay, so this gives you the double balance topology, which also gives you gain. But one might say that if this always gives me gain, why don't we use this? There is always a story behind why something is not always useful, and the reason behind this is a special kind of noise that is called flicker noise. So we have not talked about flicker noise at all. So let me give you a 2-minute primer of what flicker noise is. So just like you have thermal noise, which is the genesis of that is random fluctuation of carriers in the channel. So if you have an NMOSFET, for example, in the channel where you have carriers, and note that, and there is a region near that interface between the oxide and the channel, right? This is oxide. There is a region between the oxide, wherever the oxide is ending and wherever the substrate is beginning, right? So there will be a region where there are dangling bonds, right? Where there are bonds which are unfulfilled because that's an interface. So even though a lot of passivation, a lot of technology intervention goes in to ensure that there are no dangling bonds there are all bonds are fulfilled, but still there are. Then what eventually ends up happening is that when current flows or electrons flow from one direction to another, sometimes they get eaten up by they're captured by the dangling bond, and those bonds after some time they again release it, right? So there is some sort of uncertainty that is associated with it, and because of that uncertainty you get noise. And as it turns out, the profile of that noise is not thermal. As it turns out, that profile of that noise is, so SV flicker, this is flicker noise, this is called flicker noise, has this format. It has a format of 1 over f. Note that it's not voltage. 1 over f is the pass spectral density. The pass spectral density of this flicker noise is goes as 1 over f. And as it turns out, this is called 1 over f noise. This is proportional to 1 over f, definitely, and it is inversely proportional to W times L. That is the total area of the transistor. And note that I'm talking about the area, not W by L, right? So larger the area, better it is for noise, in the sense that noise will reduce. Smaller the area, you have larger noise, and it should be to some extent intuitive, because if you have smaller area and let's say you have same W by L, that is you have same GM, right? You can make same GM by having two different transistors, with one with bigger W, bigger L, another smaller W, smaller L, right? So if you have the same GM in two transistors, one with big W, big dimensions, then obviously the percentage of current that can change when the number of electrons are plucked out from the channel will be lesser, right, in a bigger device. So that's essentially the very top level, crude level intuition. So SIF is essentially inversely proportional to the area. but this is directly proportional to the current that flows through them. Is directly proportional to the current that flows through the devices, right? So this is a DC current, this is a bias current. So it is directly proportional to the bias current that flows through, inversely proportional to F, and inversely proportional to the to W, to the area of the device, right? So what is the designer's takeaway from this? The designer's takeaway from this is that I had to deal with thermal noise one earlier. Now I have to deal with flicker noise also. And I know that regardless of what happens, thermal noise floor will always be there. There will be a thermal noise floor. Now there is a flicker noise also. And fortunately, the flicker noise does not exist at high frequencies. And because it is 1 over F, it will eventually go well below the thermal noise floor. But if you are dealing with low frequency stuff, then beyond certain frequency, the flicker noise is going to dominate. Correct? So this, wherever this flicker noise effectively becomes equal to the thermal noise, if you just equate the flicker noise equation with the thermal noise, you are going to get a frequency number. That frequency number is also called often called the cutoff frequency, where beyond which that's forget about what it is called. It's basically the cutoff frequency below which flicker noise dominates, above which I have to bother about thermal noise, right? Okay, why are we focusing on flicker noise? Another thing is that if you go closer and closer to DC, the flicker noise asymptotically goes to infinity, right? And this has been observed, right? It's not a modeling issue. It in fact goes high and high and high and high to whatever low frequency people have observed, right? So we are not a device engineers. We are not bothered about, at this stage, we are not bothered about how to reduce flicker noise from a device objective, but what we can do is understand what we can, if we are given a device which has flicker noise, how can I use it in our circuit in order to make our transmitters, right? So you might be thinking, why should I after all be bothered about flicker noise when you are talking about transmitter which exists at low frequencies, right? Obviously there might be a flicker noise issue at the DAC level, because DAC is directly operating at very low frequency. This is not a data conversion course, so we'll not go into that. We'll assume that the data conversion engineers have done a good job and the output of the DAC has no flicker noise or low flicker noise. So we are bothered about, after the VBB has come into the mixer, what can we do, right? Now, if I go back to our passive mixer, what can I say? So in the passive mixer, what is the DC current through these switches? So you might say that DC current through these switches depends on whatever is connected at the load side. I can always connect them through a coupling capacitor, right? I can always put a coupling capacitor and block it, right? Because this side is high frequency. I can put a coupling capacitor. I can put a coupling capacitor there. I can put a coupling capacitor here, right? So that's not a problem. So what is the DC current through these switches? The DC current through these switches is 0, so there is no flicker noise. So that's a good thing about a passive mixer. There is no flicker noise, right? We don't have gain, but we don't also have flicker noise. But what about this active mixer? In active mixer, I have DC current flowing, right? I have IDC, which means I will have flicker noise, right? So now, which flicker noise should I be bothered with? So let's look at it one by one. So I'll only consider this differential pair, and I'll not consider the other half. So this guy is switching, right? So I'll just use a switch in this right now. So I have a flicker noise, just like other noise. I have a flicker noise current that goes in, right? And the flicker noise current at times goes this side, half the cycle, and half the cycle it goes that side. Correct? When I take but fortunately, the flicker noise is a very low frequency noise. Correct? So what does low frequency mean? It essentially means that if this is my LO, which I am assuming is high frequency, the flicker noise does not really change over multiple cycles of this LO. It's very slow moving noise, right? The amplitude can be high, but it's a very slow moving noise, which means what? which means the flicker noise at this during this period and during this period are identical. It's almost like DC from cycle to cycle, which essentially means that if I am getting a flicker noise current in this direction in one of certain value, I am going to get the same flicker noise current in the other arm in the next cycle. And since I am taking a differential, so that kind of gets nulled. So we do not have to deal with flicker noise of this transistor. Okay. Okay, fine. What about the switches? So let's go to the switches. So I don't have to deal with the flicker noise of this guy. So I'll just keep it as ideal. I'll just call this IDC. Okay. So what about the flicker noise of the switches? So let's see. So if I have flicker noise, I can always, just like a thermal noise, I can always model it like a noise voltage at the gate. Correct? Okay. And now consider that I have these non-overlapping inverted waveforms at the gates of M1, M2. And for the time being, consider that they are slopey. They are not infinite. They do not have infinite slope. Okay. So let's assume that this is S1. This is S1. Okay. And let's say this is S2. Let's say this is S2. Correct? So what can you comment on where, at what position of this S1 and S2 switching does the current switch from M1 to M2 or vice versa? Intuitively, I can say that it switches probably somewhere here. Correct? So if I have a flicker noise, right? If I have a flicker noise, what is going to happen? This switching instant is going to shift, right? For example, if this flicker noise is pushing this voltage up, which means that S1 will look like this at this edge, right? So and how much will this shift by? Which means that the current IDC is shifting towards M1 some time delta t before it was supposed to, and this delta t is an uncertainty. So that's the effect of flicker noise. That's the effect of flicker noise of M1, right? So we have to quantify this uncertainty, right? Or rather, we have to quantify the effect of this uncertainty. Correct? So how do I go about doing it? So can you comment on the fact that how much will be delta t given that I know how much Vn is, right? So how do I go about figuring that out? So note that here, if I look at the slope, so now I am amplifying this. So this was the original slope, right? And now this was the original signal, and now I have added delta V, right? I have added delta V to this. So the signal went on to become something like this. And what am I interested in? I am interested in finding out what is this delta T. Correct? So how much voltage did I add? I added this much voltage, right? This is the Vn. This is the Vn that shifted the waveform, isn't it? Okay. So what am I after again? I am after delta t. Did I change the slope? I took an approximation that the slope didn't change. So let's say the slope of st is s, or rather m. Because that's the general. Mathematical expression of slope. I'll maybe let me not use m because I am using m for transistor. Let me just keep it as slope. Let me just keep it as s. Okay. Okay. So or I'll just write slope. So let's say the slope is known. Then what is delta t? So slope is essentially Vn over delta t. Then delta t is Vn over slope. Okay. Okay. So that's something that's good that we know delta t in terms of Vn and slope, because Vn we'll know because Vn is a input referred version of a noise, which we know how to go about doing it, right? Okay. So what else? So what is the impact of this? So because the current is shifting to the left, the current is shifting towards M1 before when it was supposed to happen. So so I'm going to get an error, right? So what was supposed to happen? The current through M1, so IM1 was supposed to be shifting here. So IM1 was supposed to be shifting here, but now the IM1 is shifting slightly ahead. So this is the error that I am incurring. How much is basically how much extra charge I am putting in because of this error? This is basically delta T times IDC, which is Vn times IDC by slope, correct? Okay. So now what we'll do, what generally circuit designers tend to do when things become complicated, and I know that these delta T and everything is very small, we'll make a delta approximation, right? So what we'll say is, this is uncertain and this will happen every cycle. I do not know what delta T will be, but I do not even know whether the IDC will be positive or negative, whether I am undershooting or overshooting the error. So that this is the error, right? This is the, by the way, this is the error. This is the error. So if I check the error charge that is, or the error current that is going in, so that error current is basically and I express in terms of, I express this in terms of, so this is, let's say this is S of t, and I know that at every edge there will be an error current. Then I'll express the error in terms of delta, right? There will be a delta here, there will be another delta there, there will be delta here. I do not know, maybe on the negative side, something like that. But it will happen at every clock edge, and this error is basically, I am interested in the PSD of that error, correct? So if I know the PSD of the error, and this is basically a periodic waveform, all I will be interested in whatever is the error around FLO, right? Whatever is the around FLO. So without doing too much math, I can basically then say that the error PSD will be proportional to the spectrum of Vn, right? So which is 1 over f, correct? So simply I will just say, I should not say 1 over f, because this f can mean many things. I'll just say mod of Vn of f whole squared, correct, times IDC whole squared by slope squared, correct? Okay, which essentially means, I mean, this is all we need to know as a designer, right? So which essentially means that, what are the design handles? Firstly, the first design handle is, I have to increase the slope of the LO waveform as much as possible, right? That is number one. Number two is, it looks like the IDC, the DC current that is flowing through this bias current, is increasing the flicker noise. Now I cannot do anything with this, because if I try to reduce this, the gain of your mixer is going to come down, because IDC directly affects GM of this stage, right? And you have the baseband, this is IDC, this is basically converting the baseband voltage into baseband current via GM. So I cannot do much with that. What else? VNF square. So what can I do with VNF square? So VNF, note that we are doing flicker noise analysis of this M1, M2 transistor, which means I can increase the size of M1, M2, right? If I increase the size of M1, M2, and while ensuring that S1 and S2 are swinging full throttle with a high slope, then I will probably able to reduce significantly the flicker noise, right? But what is the downside to it? The downside to it is that if you increase the size of M1, M2, which means the capacitor associated with the gates of M1, M2 are large, and you want the swing at those big capacitors to be also very fast, right? Full rail to rail swing going very fast, which means you are going to have a lot of switching power. So there will be inverters which will be driving these gates, and you are going to burn a lot of switching power, which means, yeah, so you basically pay with efficiency, right? So here, I mean, already we are not even into the PA, and you see that active mixers can cause, even though you are get gain, you can have issues with power consumption. So and note that this is all happening because I have flicker noise, and flicker noise is a very low frequency noise, right? So if you are not careful, if you think that since I am operating at FLO, I do not have to bother about flicker noise, which is supposed to be at very low frequency. If I quantify, it can be as low as a megahertz or like kilohertz, right? So if depending on the size of the device, uh, so as you can see, this becomes a problem. But the good thing is, which I did not mention explicitly, flicker noise is in not all technologies, in certain technologies where you have buried PMOSes generally tend to have lower flicker noise than NMOSes, right? So if there is not much difference between the driving capability of NMOS and PMOS, that is, if mu p and mu n are not widely different, not like 3x different, there are some technologies where mu p and mu n are not that much different, and you can characterize the PMOS and the NMOSes, and you see that the flicker noise of PMOS is probably still lesser than NMOS, then it will be useful to go for a PMOS switch, right? That again, this is not a generic suggestion. This is obviously suggestion based on the technology or the topology that you have, or the technology that you have. Do characterize the technology that you have to see the strength of the PMOS versus NMOS, and also the flicker noise profile of PMOS and NMOS, right? Based on that, you can take a call. There is another issue with these type of mixers. I'll not explain too much, but let you know, so that if you are designing it, you should look out for it. So there will be a capacitor associated with this node, and if you increase the sizes of M1 and M2, right, obviously the capacitor at that node will also increase. Now when the device switches, right, so clearly when M1 and M2 is fully, when M1 is VDD and M2 is ground, then M2 is cut off and M1 is in linear. But whenever M1 and M2 are close by around switching thresholds, then both of them are in saturation, right? So this node will not be in a virtual ground state. This will move, and if you see, this will move like this at twice the FLO. So this will be TLO by 2. And because this is going to move, right, there will be a current that will come through this capacitor, which is non negligible now. And now the flicker noise of M1 and M2 gets a path to flow through this capacitor and hence come out also, right? So that is something, I mean, I'm not proving this because of lack of time, but you can get the idea that having very large devices can cause a flicker noise to come out, right? So that is something that again you have to be careful of. So crux of the story is you get gain using active mixers, but at the cost of flicker noise and power. You do not get gain in passive mixers, but you also do not get flicker noise, right? So that is something that you have to be aware of. What about linearity? I mean, it's basically a bunch of switches. So as long as you have large enough overdrive, you have in the switches, you have good linearity. If you do not have large enough overdrive, you will have poor linearity. The body wire sometimes can help. Basically, we'll not get into these things in detail in this course, but sometimes you can modulate the body wires voltage to ensure that the threshold voltage reduces when, I mean, if the threshold voltage reduces, then obviously the amount of overdrive you require to drive a signal will be lower. So some tricks can be played in those directions. However, you have to be careful with the breakdown and forward bias junctions and all those things, right? Okay, so we'll stop here.